Alright, we're trying to explain the car crash analysis that we did. It wasn't really an investigation or a lab, but we were trying to look at it as far as a problem-based learning. So it says when you're courting a nice girl, an hour seems like a second. When you're sitting on a red cinder, a second seems like an hour. That's relativity. Now that's relevant because we're actually going to talk about relativity in terms of motion towards the end of this lecture. So, the learning goals. We want to determine situations in which time is not easily measured. Usually those are things that are after the fact, like car crashes. We want to be able to show the origin of the fourth motion equation and determine an unknown for this equation that we're referencing here. We also want to be able to recognize motion relative to different frames of references. In other words, two objects are going in the same direction, opposite directions. We want to be able to figure out the motion between them. So, car crash analysis. So far, you looked and said, okay, time is impossible to measure after an event occurred, and you're giving the example of a car crash. And we use this formula as far as the insurance formula to say, hey, how fast were they going if you have these variables right here? So, this is something that we use. It's kind of a manipulated version of what we can actually do. If you take a look for an equation without time, we take our two original equations that we had, one for average velocity and the one for acceleration. These are kind of our two mainstays. If you expand this one out and you rearrange this one to solve for time, you can actually eliminate this equation by taking this equation, solve for time, and plugging it in there. And you can actually get the equation that you see right here. Now this looks like it's of absolutely no use, but when you figure out from Algebra 2 that you FOIL this, you do the first, inner, outer, last, when you multiply it out and you FOIL it, what you end up with is this equation right here. And that's A equals VF squared minus VI squared over 2D. Now, we've covered all these variables already. We've covered A, we've covered VF, we've covered VI, and we've covered delta D. So you really shouldn't have any sort of problems as far as giving them their names, their definitions of what they're measured with. Remember, the units are the key though. Meters per second squared, meters per second, and meters. That's how you're going to identify your given information. So, in this first example, it says a driver sees a cat in the middle of the road 20 meters ahead and immediately slams on the brakes. The driver has a known reaction time of 0.34 seconds and was initially traveling at 12 meters per second with a maximum deceleration, with deceleration being the key there. Will the driver stop in time? Alright, in this example we have a cat who is 20 meters away from a car, hoping he doesn't get run over. The cat's initially 20 meters away from the car, and the car is traveling in the direction of the cat at 12 meters per second. Okay, it says that we have where it slams on the brakes after a reaction time and has a deceleration, which means it goes in the opposite direction of 5 meters per second squared. So now let's take a look at our given information. We actually have a couple of different situations right here. We have situation number 1, which is when the car travels at a constant velocity. That's during the reaction time. And then we have situation number 2, which is when the car is decelerating. Okay, it's going to travel two different distances, a distance while it decelerates and a distance when it travels at constant velocity. Now the total displacement of the car, we actually have to take those two distances and add them together. So let's take a look at what our given information is. First of all, we're going to take this and we're going to divide it up into two things. We're going to divide it up into when it's traveling at constant velocity and when it is decelerating. So, to begin with, we know that it's traveling at 12 meters per second. It is a constant velocity for 12 meters per second, so we know that that is going to be the only velocity that's there. The reaction time that it gives is 0.34 seconds, so that's how long you have while you're traveling at 12 meters per second before you actually step on the brakes. As far as while we're decelerating or while we're braking, we know that we had an initial velocity of 12 meters per second. We know that we're going to have a final velocity of 0 because we're going to come to a stop. And we know that the deceleration of the car is 5 meters per second squared, and that's opposing the motion of the car, so we know it's going to be negative 5 meters per second. So now, we are trying to solve for the displacement. And we're going to say d total. That's what we're trying to solve for there. We're trying to find the total displacement of the car.
we know that we actually have two different situations here. We're using constant velocity and we're using if that. So, whenever we take a look at constant velocity, the equation that we use is v equals delta d over delta t. And when we do if that, we can take a look at here and we can say, okay, I'm trying to solve for a displacement. Okay, I know that I have an initial velocity and a final velocity, and I'm trying to solve for, I also have the acceleration. So the equation that doesn't have time in it at this point is the one that we're looking at for this section, is a equals vf squared minus vi squared over 2 delta d. So we look and see, is there any irrelevant information? Well, I'm trying to solve for displacement here and displacement here. So I look at my variables. I've got velocity and velocity. I've got time and time. I've got initial and initial. I've got final and final. And I've got A and A. And so everything checks out. There's no extra information. So now we can start to solve for this question. We're going to start off by solving for our constant velocity part. So our constant velocity part, we have the formula v equals d over t, or 12 equals delta d over 0.34. We rearrange by multiplying both sides by 0.34, and when we do that, we end up with a displacement of 4.08 meters. So that's how far the car actually travels before he recognizes the cat and pushes the brake. Now, we look at the deceleration distance. The deceleration distance, we know that we're going to use the formula a equals vf squared minus vi squared over 2d. And we start to plug in our numbers there. So we start off with the idea that we have -5, which is our deceleration, equals the final velocity is 0, so 0 squared, minus the initial velocity, which is 12 squared, divided by 2 delta d. Okay, the first thing that you want to do is you want to isolate this delta d term. So in order to do that, I'm actually going to multiply both sides by delta d. And when I do that, I'm going to end up with -5 delta d equals, and I'm going to start to simplify this a little bit. So I know that 0 squared, put a little line right here, the 0 squared is 0. I know that 12 squared is 144, and then I know this right here is going to be 2 because we moved the d over. So now I'm going to say, okay, let's simplify it a little bit more. I'm going to turn this into -5d equals -72. Okay. Once you do that, you can now start to solve for this. You divide both sides by -5, and when you divide both sides by -5, you end up with a displacement of 14.4 meters. So now you have these two distances right here. Remember, we were trying to solve for the total distance. So we actually need to take these two distances right here, and we need to add them together. And when we do that, we'll get our final answer. So we'll get the total distance is equal to the two distances added together. So we take those 4.08 plus 14.4, you add those together, and then you do your significant digits, and you end up getting 18.5 meters. Okay, in this question it says, what is the maximum height of a ball thrown upward at 35 meters per second? So, it looks like we only have one piece of given information here, but if you remember back to what it says at the maximum height, we say we take a ball, we throw it up, and at the very top part of its path, we know that its velocity is 0. Okay, we also know that the acceleration is always -9.8 meters per second squared. So with those two pieces of information and the 62.5 meters. This one says a car accelerates from rest to 85 meters per second at 400 meters. What is the acceleration of the car? You should be able to figure out that the acceleration is 9 meters per second squared, and you should be able to do that using the information in the problem. Now, objects aren't always, it's not always just one object. A lot of times objects are moving relative to each other.
So if we were to take a look at this motion of the figure on the right and just describe his motion, he's clearly standing still. But that's because he's standing still on Earth just like you are. Remember that the Earth actually travels around the Sun and it spins on its own axis. So even though it looks like you're standing still right here, upside down, really you're spinning along with the Earth and you're revolving around the Sun. So there is no really way to take a look at it and say, I'm absolutely still. It depends on where you actually observe the motion from. So, if you look at it, you would say these figures are motionless, but it's only motionless relative to you in the classroom. Motion depends on where the system is being viewed from. So because of that, there is no what we call absolute frame of reference. And we're going to reference that later in the year. There's no absolute frame of reference. So what that means is it really matters where you're observing the motion from. Now, unless otherwise stated in a problem, we're going to assume that all motion is observed from Earth. So in other words, when you're standing still, we're going to say, yeah, you're standing still. We're not going to take into account the motion of the Earth spinning or revolving or anything like that. So unless otherwise stated, you're going to keep it what you generally would think of as your frame of reference. Now, frames of reference relative to each other. So if you have a car A that's traveling at 20 meters per second west relative to Earth, and car B is traveling 22 meters per second relative to Earth, from car A's perspective, it looks like car B is traveling at 2 meters per second west. So in other words, it looks like car B is creeping up at 2 meters per second on the orange car. Because from the orange car's perspective, it looks like he's not moving at all. But from car B's perspective, if I'm in car B right here, what it looks like this orange car is moving backwards at 2 meters per second. So even though it's the same magnitude, it's very different directions depending on where I'm observing the motion from. For these frames of reference questions, it's really important that you draw out the picture so you can see what it's going to look like from a certain perspective. Now, another example, this is car A is traveling 20 meters per second east, car B is traveling 20 meters per second east. If you were to take a look at it, it looks like they are moving towards each other at 40 meters per second. Now, if you take into account the fact that if I'm in this car, it appears motionless, it appears to me like this pink car is moving to the east at 40 meters per second. Whereas if I'm in this car over here, it looks like the blue car is traveling towards me at 40 meters per second. But in other words, when these cars are headed towards each other, the effect is additive, and whether or not it's coming towards you depends on your perspective. So it's really, really important to draw these out. Another perspective is this. So we've looked at cars headed towards each other and cars going in the same direction. But now, if we take a look at it in terms of a plane and a tailwind, or a plane and a headwind, if you take a look at it, the plane is moving at 150 meters per second relative to the air. But the air itself is moving at 10 meters per second in the same direction. So because of that, it actually provides an additional push that makes the plane move 160 meters per second relative to the ground. You've probably seen this in a situation if you've ever been on an escalator or what they're called people movers. It's basically a flat escalator that it actually moves you along at something like 2 meters per second. Well, if you walk along that, you're moving at, let's say, 3 meters per second relative to the people mover. But the people mover is moving at 22 meters per second relative to the ground. So relative to the ground itself, you're actually traveling this way at 5 meters per second. So you've got to take into account, it's really important that you draw these out and you kind of look at it and say, okay, what's affecting what in this given situation? In this question it says you've got a car that's stuck behind a large bale of hay on a single lane highway. It says the truck is traveling at 45 miles per hour on a 70 mile per hour road. We've all been here. You want to know if you've got enough time to pass the truck and not see another car coming the opposite direction.
So there's 250 meters in between you and the car, and you quickly step on the gas to accelerate it up to 70 miles per hour, and you stay at 70 miles per hour until you pass the 20-meter long truck. It's got a really long bit of bales of hay. And you want to know if it's safe to pass the truck, and it wants to justify your answer with equations. So you want to know, hey, can you go ahead and pass this truck and make it in time in this 1,000 meters that's in between you? Okay, this is a tough question. It's got a lot going on, so let's take a look at what we've got. The first thing we want to do is we want to identify our given information for the different cars. So to start off with, we know that the blue car is going to travel at a constant velocity the whole time. That constant velocity is 70 miles per hour, or whenever we convert it, we know we're going to have that as 31.3 meters per second. You should be familiar with conversion by now. So 31.3 meters per second. Now if we take a look at the truck, remember the truck travels at a constant 45 miles per hour, or 20.1 meters per second the entire time. That's the velocity of the truck. The black car has a lot more kind of going on. It's accelerating. It says an acceleration of 5 meters per second squared. It says it starts off at 20.1, which is that 45 miles per hour, and then it actually accelerates to 31.3 meters per second. And so we kind of go from there. We know that overall what we want to know is we want to know the total displacement between the black car and the blue car. So how far they move relative to each other, and we want to make sure that that number is less than 250. So the principle involved here is going to be if that, and then we're also going to use constant velocity and a relative velocity. This question, like we said, has a lot going on. So the first thing we want to realize is that the formula that we're going to use is V equals delta D over T. We're also going to use several if-that equations, so let's just kind of take a look at it from there. The first thing that we need to do is we need to calculate how long and how far this car travels whenever it passes or whenever it gets up to the 70 miles per hour. So we're going to take a look at the black car first, and we're going to say, okay, the first thing we want to do is we want to know how long it's going to take for this car to pass that car. And it's a lot easier at this case. Instead of saying, hey, this is 20.1 and 31.3, you can make it relative to each other. So the black car is actually traveling at 20.1, or zero relative to the red truck to begin with. Well, for now, we'll just leave it in regular terms so we don't get confused. So the black car, acceleration equals final velocity minus initial velocity over time. And the acceleration of that car is 5. Its final velocity is 31.3. Its initial velocity was 20.1. We take that, we divide it by t. We rearrange, and we end up with a delta t value of 2.24 seconds. Now that's how long it takes for the car to actually travel to get up to this 31.3. We also want to know how far it has to travel. And to do that, we use the formula A equals VF squared minus VI squared over 2 delta D. Well, during this time right here, it's traveling, we would say A, which is 5, equals 31.3 squared minus 20.1 squared. All of that would be over 2 delta D. We'd rearrange and switch this with delta D. And what we'd end up with, as we calculate this whole thing out, is we end up with a displacement of 12.54 meters. Well, that's a problem in the sense that I've got 20 meters in between the car and the truck, and so if I only travel 12.54 meters, when I get up to 70 miles per hour, I still haven't passed the truck yet. So what I need to do is I need to take a look at it is how much further do I have to go? Well, this is still that black car. It needs to travel 20 meters, and it's only traveled 12.54. So we need to subtract those two, and now we get a displacement. The displacement that we get is 7.46 meters. So I need to travel 0.46 meters that it's traveling is still traveling relative to the red truck. So because of that, the velocity that they actually travel relative to one another is this, you have to subtract those two values, and that's 11.2 meters per second. So now you can say I've got a velocity of 11.2, I've got a distance of 7.46, and you can solve for your time. You switch those two terms, you take 7.46, divide by 11.2, and what you're left with is a time value of 0.67. Okay, now once you do that, you can take this time and add them together. When you do that, that gives you a total time of 2.94 seconds, which means that the blue car is traveling at 70 miles per hour for 2.94 seconds. So now you can say, okay, well the blue car travels at 31.3 meters per second. The displacement is what we're looking for, and it travels for 2.94 seconds. We can say that the blue car travels a total distance of 91.1 meters. So now we know that the blue car travels 91.1 meters. So now we need to figure out what the displacement of the black car is relative to the ground as well. So now let's take a look at it. We say, okay, we have a total displacement that we're trying to solve for. We know that the initial velocity relative to the ground was this 20.1. We know the final velocity is 31.3. So now we say, okay, 1/2 of 31.3 plus 20.1, and now we can multiply it by this total time factor that we have here, this 2.91. Okay, and when we multiply that out, we get 0.5 times 31.3 plus 20.1 times 2.91, and we get a total distance of 74.8 meters. So the total distance that it travels, the black car travels 74.8 meters, the blue car travels 91.1 meters. So the total distance relative to each other, you have to add those two things together. And when you do that, you get 166 meters, which is less than the 250. So it is safe to pass the car. In this question, it says a Boeing 747 takes off at 7:04 and it completes a round trip. It says the plane experiences 15 meters per second of headwind for the duration of the trip. It says it has a cruising velocity of 565 and that you allow 30 minutes for passengers to get on. And it says, when can you expect to land in Houston? Okay, remember this is going to be a round trip. This is a round trip from San Antonio, or excuse me, from Houston to San Antonio. So you got to start here, you got to travel to San Antonio, you got to travel back. Now you have to take into account the wind in this particular case. So you want to split this question into a to San Antonio and then a back to Houston problems. Now you can assume that it's traveling at a constant velocity. So our equation is going to be v equals delta d over t. Now that's probably not the case, but there's no acceleration numbers, and it's probably an insignificant value in terms of the overall time. So you're trying to solve for the total time it takes to go from San Antonio to Houston and from Houston to San Antonio. And you have to take into account the direction in each case. When I'm going towards San Antonio, it actually adds to the velocity. This extra 15 meters per second is additive. And when you're going back to Houston, it's going to take away. Now it's very, very important that you get these things into standard units. This right here has to be into the standard unit of meters per second. In addition to that, you need to know that the distance between San Antonio to Houston is 215.5 miles. When you take all this information, you add it all up together, you do your calculations, you can expect to arrive at 8:20 p.m. back in Houston. This is a people mover, moves you towards an airport gate at 4 meters per second. This is a relative velocity question. You should be able to figure out that you would save 75 seconds by walking